Sorry about that. The first paper we are going to listen to today is on an approach for efficient planning of robotic manipulation tasks by Richard Dearden and Chris Burbridge. And it's Richard who is presenting right now.
Okay, thank you very much. Normally I wander around and gesture a lot, so I'm going to try and be restrained and just stand here. Actually, to be honest, if I stand here for 25 minutes, I'm going to have a tan with how bright this light is. So this is some work we've been doing as part of an EU project, which is, well, I'll tell you a bit about the EU project in one of the slides. But the stuff I really want to talk about mostly today is the planning stuff, but I'll give you an overview of the whole project because it gives some insight into why the planning is the way it is. So basically, we're interested in manipulation planning, and the problem is that, I don't need to tell anyone in this room, what makes it difficult is the hybrid nature of the problem, right? So you've got, you want to do symbolic planning because you'd like to find different solutions to the problem, right? You don't want to, so what people often do in this field is that they just assume that this is a geometric planning problem, and so they kind of, the goal is, this is the goal geometry, and all they have to do is manipulate the objects to get them to the goal geometry. But if we want to allow different solutions at a symbolic level, that allows us to have different ways of accomplishing that goal. And so we'd like to do both of those layers of planning, but then the problem is if you plan in that completely, you do an awful lot of backtracking, generating geometric solutions for parts of your symbolic search space that actually you're never going to execute because they're not on the path to the final plan. And so what we were interested in is seeing how much leverage we could get without having to go for the full hybrid planning and sort of generate a step in your symbolic state, turn that into a geometric step, see if that worked, if necessary backtrack, and so on. So we were trying to do as little backtracking as possible because the expense is really in in turning that symbolic plan into a geometric plan in these kinds of problems. So the overall project, the idea with GERT was essentially we've got a robot. In this case, this is Justin, which is DLR's super fancy, it's an amazing robot actually. And they have a couple of guys who write really good hand-built programs for this thing. And they've got a whole library of these programs, right? If you go on YouTube and search for Justin Tea Robot, you can watch it making tea. There's a video of it making coffee. It throws and catches balls, does all sorts of things. And they have a big library of these hand-built programs, and what they'd like to do is essentially take these pieces of Python code, extract actions out of them, and then reuse them to solve novel tasks. And that was really the whole idea of the project. So from a planning and a learning point of view, the idea was to learn actions which we could then plan with in these geometric sort of robot manipulation domains. And what we're going to do is we're going to learn not just the actions, but also the geometric predicates that tell us what's happened in the world. So the idea is you're going to learn that, say, one object is above another, or touching another, or something like that. Use those predicates to learn the actions, and then use those actions to plan with. And we'll cover that a lot. So this is kind of the overall system, right? We start with the example programs over on the left. From those, we're going to generate learned actions, and we're just going to learn standard PDDL models of the actions for now, and corresponding fragments of Python code so that we can take an action in the plan and generate code from it. And at the same time, we're going to use the simulator to learn these geometric predicates, which are the predicates we're using to describe the actions. And then the combination of these can then, along with some new goals, can then be used to generate a new plan. So just to have a little look at the predicate learning, essentially what we have is, what we want to have is a symbolic state representation that tells me geometric information about the world. So we want to be able to say that the cup is above the tray, that the tray is touching the table, that the cup is upside down, etc., etc. And so what we're going to do is, because we want to learn these things, we need a very low dimensional, or as low dimensional as we can get away with, representation of these things. And so we choose this essentially we put bounding boxes around the objects, and then we look at the relative positions, rotations, and sizes, so scales of the objects, and we use that as the space we're learning in. So when we learn these predicates, what we're going to do is we're going to take the example programs, we're going to generate the states at various points in the programs. We're going to ask our programmers to just label the program, so put little annotations in the program saying, oh, at this point, cup number 2 should be above and touching the table, and the tray should be on the table, and etc., etc. And then we're going to use that as labeled training data to learn these representations of the predicates in this, what is going to turn out to be this sort of continuous space of positions and relative positions and sizes of the objects. So for a 2-object predicate like above cup tray or above xy, we end up with a 17-dimensional vector that we're essentially trying to learn these concepts in. For a single predicate object like upside down cup, then we end up with just a 10 dimensions, so basically the size, rotation, and position of the object. So what we do is we learn this as a kernel density estimate, and the reason we do that is because we can use it in both directions. So when we want to do a classification task, that is, take a geometric state and extract a symbolic description of that, well, it's just a kernel density estimate, so all we do is we measure the probability according to the learned KDE of the particular state of the particular geometric state we're in right now, and we just threshold that and say anything where it's higher than 80%, we'll call that, yes, this predicate is true, and if it's lower, we'll say the predicate is false. But we can also use it in the other direction, right? We can do hill climbing in that probability distribution to find high probability geometric states that correspond to some sentence in the symbolic language. So now we can generate our initial state by using it as a classifier, but we can also turn symbolic states into geometric states by doing this hill climbing procedure. And the really nice thing about that is we generate the same kinds of states that the humans do, right? So when we, for example, we're going to see a lot of examples of cups on trays in this talk, and when we ask it to generate positions for the cups on the tray, we typically end up with the same kinds of positions that the humans choose. So we don't end up with the cups right at the extreme corners of the tray where, they're potentially less likely the actions are less likely to succeed. Okay, so the other thing, of course, we need to do, as well as doing this hill climbing, we also need to support backtracking from the planner, and then we do a really simple solution to that. When we've generated a geometric solution, if we're going to backtrack over that, we just put a sort of an inverted Gaussian at that particular point in the continuous space and hill climb on that instead. So in the pictures at the bottom there, the first one we've placed a cup on the tray, and for some reason we've caused backtracking, and now we're going to hill climb in this new distribution where red are high probability points and blue are low probability points, and you can see where that first cup was. Then we've generated a second solution in the middle picture, but again, we're not happy with it, so we backtrack again, and so on. And in the right-hand side picture, we've generated 6 different positions for the cup, and now we're saying, well, see if you can find a 7th one that's sufficiently high probability to make the predicate true. So it gives us a lot of flexibility to support all the kinds of things you want to do in planning in terms of translating from the symbolic to the geometric state. Okay, so then the action learning, and this is the bit that we haven't actually kind of pushed particularly hard. So what we do is we essentially split up the example programs at the points at which one of these geometric predicates has changed. So we look for places where the geometry changed. We assume that all of the code from the previous change to there is one action, and we package that up as the action, and we expect, again, the programmer to annotate the code to give us a little bit of a hand in doing the generalization, right? So if we have something, so here, on the left-hand side, this is something doing something to the tray, and we tell it the tray is an argument, and every time you see tray, you should substitute in whatever the argument is from your action. So that's how as I say, there are better things we could do for this, but we haven't pushed on this particular bit very hard. Okay, so now we'd run the thing in simulation, we detect when these geometric states have changed. So in that first one, the milk carton is on the tray, and in the second one, Justin has now picked up the milk carton, and so there's a change in the geometric predicates. It's no longer touching the tray, and so that would trigger a separation from one action into another, and then we can generate preconditions and effects just by looking at what was true beforehand, what was true afterwards, and obviously generalizing over all the examples of this piece of code that we have. Again, well, I'll say some more about this stuff in the future work section. So now I want to get onto the planning stuff, and as I said in the beginning, the key point is that when we're generating these plans for the robot, there are 3 parts to it, and we want to try and do as little of the expensive parts as possible. So in order to generate a plan, we have to generate a symbolic plan for the goal that we have. We then have to turn that into geometric positions for the objects, and then we have to check that we can actually get the arm to go to the positions we want and place the objects without intersecting other objects in the scene. Depending on the symbolic plan you generate, obviously you might end up being unable to generate a geometry, you might be unable to generate paths, and all of those are going to trigger replanning in the sort of previous levels in this hierarchy. And as I said, the whole idea here is to see how far we can get without integrating all of these together and doing it as a full hybrid plan. Okay, so I've pretty much said all of this stuff, right? So in fact, I've said pretty much all of that stuff. So what we're going to do is we're going to plan this hierarchically. We're going to treat it as do the symbolic plan, then turn it into geometric positions, then do the path planning. But we are going to allow some limited backtracking, and I'll show you exactly how we do that. But essentially, if we can't generate geometric states, we're going to change the goal for the symbolic planner and let it try and plan again. Okay, so here's the picture, right? We have our planning domain and our goal. We put that into the symbolic planner. We generate a symbolic plan. We add geometry. If that fails for some reason, so add geometry is doing this hill climbing and the learned predicates. If that fails for some reason, we're going to figure out what we couldn't generate geometry for and add that into the goal, or add the negation of that into the goal and call the symbolic planner again. And once we've achieved that, then we'll check to see in the simulation environment whether we can actually execute the code that we've generated and without having collisions with other obstacles or internal problems with the robot arms and things like that. And if it passes all of those tests, and again, that could trigger replanning in the geometry, and eventually if we replan too many times without success in regenerating the geometry, symbolic backtracking as well. And hopefully at the end of that whole process we get a good plan that's ready for the real robot. So here's just a little example, right? So in this case, our initial state has a couple of cups on the table and we want to place them on a saucer, right? So there's probably not room for 2 cups on the saucer. And we generate a plan that just has it pick up cup 1, put it on the saucer, pick up cup 2, put it on the saucer. This probably isn't going to work. So now what we do is we run the hill climbing to generate the geometric states, and the chances are in that situation that the hill climbing will fail because it just can't squeeze the cups on the saucer. If it did succeed, then the path planning will probably fail because we won't be able to get both cups on the saucer with the robot hand in the thing as well. So, but the key point is we do this when we do the geometric plan. When we generate the geometric plan, we do it backwards through the plan. And the reason we do it sort of starting at the end of the plan is so that we're planning geometric locations for as many of the objects that we manipulated as we possibly can in one go. So rather than have a plan, so in this case, plan a position for the first cup, then given that plan a geometric position for the second cup, we'd rather plan both of them simultaneously. It turns out it's a lot more efficient to optimize the positions of the 2 of them simultaneously, and then sort of work our way back through the plan and look for other places where objects have been moved. Okay, so and the other key point of this is because when we're doing this hill climbing over a sentence in our symbolic language, right? So in this case, we want cup 1 to be above the saucer and touching the saucer, and cup 2 to be above the saucer and touching the saucer. We've got 4 predicates in there. Each of those is a 17-dimensional vector, right, in our representation. But actually, the saucer hasn't been moved, so its position is fixed. And the predicates share lots of other arguments. So in fact, the optimization or the hill climbing only has to be done in the space of positions and rotations of the 2 cups, which are the only things that have been moved to this point in the plan. So even though in theory there's 70-odd dimensions in this problem, 78 in fact, no, 68, there's only 14 dimensions we care about because all the other ones are fixed by the fact that we haven't moved those objects in the plan. So we only have to do our hill climbing in this 14-dimensional space, which makes life much, much easier. Okay, so I have a little video coming up, but before we start the video, I'll just explain what you're going to see. So in this case, we've got a tray that's very cluttered already. It's got lots of objects already. And we're going to add, the goal is to remove this additional cup that he's picking up now and put it on the tray. And the colors you can see are the probability distribution over where the cup could be. Okay, that should be fine. And so what we see is it trying multiple positions for the cup, but in each case, when it tries the path planning, it discovers that it can't possibly put the cup there because it intersects other objects. And so after a number of attempts, it backtracks to the symbolic level, generates a new symbolic plan, and this time the symbolic plan involves turning the cup upside down and sticking it on the sugar container. And so now this time it says, yep, that's a plan that'll work. And so now we execute it on the real robot, and by some miracle, the cup actually stayed on top of the sugar container. It was supposed to stack it in the other cup, but yeah, so here we go. Oh, and the video stopped before you saw it. But yes, it just manages to balance it on the sugar container. So yeah, we generated this first plan, couldn't find a solution to that one, and then went back and generated the second one. Okay, so I have about 5 minutes left, so I'll show you the results really briefly. So the problem with doing stuff with real robots is it's very hard to do lots of nice results. So what we did was we wanted to explore when we had to do backtracking and what the costs were in terms of total time. And so we sort of started with these 6 different tray configurations, starting with sort of where A was pretty empty and F was pretty cluttered already, and then we added between 1 and 4 cups to all of these situations. And in most cases, the first plan that was generated was to try and put all 4 cups on the tray, and then the subsequent plans would be to stack 2 of the cups, one inside the other one, and try solutions like that. And I'll just pull out some of the more interesting results. So the first one is, it actually works surprisingly well, even on cluttered trays. If you don't have too many objects to place, it's really quick, right? So we can add a single cup to pretty much any of those trays in about 6 seconds. That's the total time for the symbolic planning, which is really fast, right? Because these are pretty small plans, plus the geometric search, plus the path planning, which is actually the slowest part of the entire process. The other thing that's good is that the geometry generation is approximately linear in the number of objects. So here, as the number of cups goes up, we get a relatively straight line in terms of the time required to generate those plans. So these are in situations where there's no backtracking. So you just generate a single solution that works. The one other interesting case I wanted to pull out is this top one where we've got a cluttered tray, we're trying to add 4 cups to it, and we actually get 3 different outcomes. So in 40% of the runs, it just can't generate a plan at all, and we just ran out of, we limited the number of backtracks it did, and it ran out of backtracks. So in this case, it generated, first of all 4 cups on the tray, and then it tried stacking 2 of them, still couldn't put 3 cups on the tray, so it tried a different pair of cups to stack, and it just kept on generating those solutions until it ran out of backtracks. In 10% of the cases, it managed to squeeze somehow all 4 of those cups on the already cluttered tray, and in the rest of the time it then nested 2 of the cups and managed to get 3 stacks of cups on the tray. Okay, so a few last words. I said all of this stuff before. I think the idea of having a proper symbolic planner on top of the geometric planning is actually really important. I'm not claiming that we did it first, but convincing the robotics guys that the goals for these kinds of manipulation tasks is not just a geometric configuration is quite challenging, but I think it's really important to consider that there are multiple geometric configurations that would meet a particular goal. And as I said, the learned predicates really provide a very nice solution to this, because we get natural solutions, right? We end up putting the cups in sensible places. And what we would claim anyway is that that most problems don't actually need the full power of hybrid planning, right? You don't need to consider the geometry while you're generating the symbolic plan, because in many cases it's actually pretty easy. You know, we can, you know, even for 4 cups on that already cluttered tray, 10% of the time it just squeezed all 4 cups on there and said, hey, you know, why not just generate this as a symbolic plan? The geometry generation and the path planning are by far the most expensive part of this, so if you can do them less, that's got to be a good thing. And yeah, and then so in terms of future work and limitations, so one of the key things that makes this slower than it could be is that we're really only, when we plan the geometry, we're only taking into account the objects that are in the plan. And so in the case of that very cluttered tray in the video, right, it was trying to put the cup in places where it was never going to go because there was another object that it would intersect with. And we'd like to be able to recognize that during the optimization, but there's a trade-off that you're making between how complex your hill climbing for the geometry is versus the backtracking and the planning. And it turns out that, well, we have to be clever about doing that bit, I think. Then the second thing is that all of our plans assume that the actions are reliable, and in practice, when you run it on the real robot, things don't end up in the places you planned them. And so some of the time we have to rerun the path planning at runtime, which is obviously very slow. And we've been playing around with using a POMDP-based repair planner to do that bit, but it's not in the ICAPS paper, so come and ask me about it later. And then the other thing that I wanted to say is that the action learning, you know, as I said at the time, we didn't do all of the stuff that we could have done there, right? We haven't really pushed on that part of it. So we've been doing a bit of work trying to use a physics simulator to generalize. And in fact, in the video, that thing where it sticks the cup on top of the sugar container, that was actually a generalized action that it had learned, right? It had sat there in the physics engine trying this thing and going, yep, that works, no, that doesn't work, and figuring out how it could generalize the action. But there's a lot more work that could be done there. And also, obviously, we'd like to reduce the amount of annotation that the programmers have to put in their programs, the hand-built programs, when they write them. And really, for that, you just need a lot more data. You need more programs, and then I think you can do a lot with that stuff. So thank you very much for your attention.